Are there any questions?
I think I have a question about the project that's due.
The chapter 11 through 14?
Yeah,
Okay.
I don't understand.
As in what you're supposed to do?
Yeah,
All right. So the assignments for chapters 11 through 14 are out there. So if you go to Blackboard under chapters 11 through 14, textbook homework assignments, if you click on that, you'll find a spreadsheet with your name on it. What are the chances I can easily access it here without having to log in one more thing? I'm going to click on the don't ask for 30 days. Who knows? It might actually work. Let's see, states of matter. Individual assignments.
oh,
All right. So, for example, we have a column here that says Robert at the top. I don't think I have any repeating of names. I have had that before, but it's basically listed in alphabetical order based upon your last name, which is not listed here. So this 11 point, all of it, 11.039 means chapter 11, problem 39.
oh.
This is chapter 14, problem 78.
Okay. So you just want us to do the homework problems and that's it for those chapters?
Yes,
No
Yeah.
master set, no quiz?
correct. No master set, no, this is the quiz
Okay.
for that particular one.
What does that do?
It is due, you scroll up some. It is due by Thanksgiving break.
So anytime.
That's good to know that.
Yeah, but it's 1 day, 2 days.
When is Thanksgiving?
That's what I'm saying. I know we know.
Somewhere near the end of the month, I went through this discussion before and I've forgotten already.
Around Thanksgiving.
What is it?
It's around Thanksgiving.
Yes,
It's somewhere
it is
between-
around Thanksgiving.
The last day of class is the 26th, November 26th. It's the Tuesday.
Yeah,
We
all
won't
right.
have class Thursday or Friday. There's no school,
Answer my question. That's what I was asking.
right?
To my knowledge.
To my
Yes.
knowledge, there's no school.
Okay, so we have class on the 26th?
Yes.
Okay,
Is there school
So-
that Wednesday?
I don't think there's school that Wednesday. I think it's closed
Which
Wednesday.
doesn't
Friday.
affect this group, but,
Yeah.
well, I guess it would affect it because if there is school on Wednesday, then you can hand it in on Wednesday.
There's no school. It said closed Wednesday.
All right. Other questions?
That explains a lot, thank you.
Okay.
I was very, it said 11.043 and I was like, what's going
Your mind reading skills just absolutely wrong.
on? They're like, beep, beep, beep.
no, this is.
All right.
Thank you.
Other questions? All right, so now let's begin chapter 15, thermodynamics. Suppose I have some system here, which has a certain amount of energy in it, which I will cleverly label E sub I for the initial amount of energy. And it could be this room, it could be, a thermos. There's some confined space. And into it, I put energy into it. And some energy comes out of it. And so I end up with some final amount of energy. So if my final amount of energy is just going to be whatever I started with, plus whatever I stuck into it, minus whatever I took out of it. I'm hoping this is not a strange concept. If you think of it in terms of money, the amount of money I have at the end of the day is, well, it's whatever I started with, plus whatever I was given, minus whatever I spent. Now, of course, we can't leave it as simple as that. We gotta make some changes. Well, first off, I'm going to subtract the initial amount of energy from both sides. So I have E final minus E initial is equal to the energy in minus the energy out. And if I've got final minus initial, how do I shorten that?
Can you say that again?
Delta E.
Yeah. If I have final minus initial, how do I shorten that? And that's just the change in energy, or as was said, delta E. Now the energy that's coming in, since this is thermodynamics, we need to think about how does energy actually get transferred from one object to another. And when you're dealing with thermodynamics, that energy coming in comes in because of a difference in temperature. And of course, we have a brand new name for that one, and that is called heat. Heat. Energy transferred. Transferred because of temperature difference. And as you would expect, there's a symbol for it. And the symbol is obviously a capital Q. I believe it stands for quantity of energy. I think that's how they originally came up with Q. So the energy in is Q. And the energy out is I've got this object that has this energy, it's going to do something with it. And it's basically, it's going to get rid of its energy by doing work. And so minus work. Now we can get even fancier here, or a slightly different shortcut. This is the first law of thermodynamics. It's just conservation of energy. I substituted for Dr. Williford a couple of years ago, and they were basically doing this energy conservation. And man, the way the book described it was just so complicated. Matter of fact, almost every book that goes to describe it makes it far more complicated than I think they need to. It's just, I start with energy, I put energy in, I take energy out, I end up with a certain amount of energy. It's as simple as that. However, of course, physicists aren't going to sit down and do this without saying, you know what, how could we make this more complicated? Yeah, I know. The way they make this more complicated is I did this in terms of I have the system right here with energy in, energy out. To me, this makes the most sense. However, not everyone agrees. Some people, instead of looking at it from this point of view, look at it from the environment point of view. And so this energy in is actually energy out from that point of view, and that's energy in from that point of view. And so you'll see variations of this with different pluses and minuses. Thermodynamics textbooks that I've looked at usually start out with, here's the convention that we're using, because at least they acknowledge that it's different in different places. But we're going to settle for this right now. We're not going to get into the weeds so much that which system we're looking at, whether it's looking at the small thing or the large thing, is going to make any
make any difference. Dramatic pause for questions. All right, let's break down that change in energy. What are the two types of energy that we care about?
Potential.
All right, so if I have a change in energy, that means I have a change in potential energy or a change in kinetic energy, or both. Kinetic energy deals with movement. So if kinetic energy changes, either the mass changes or the speed changes, and or. But I have basically two ways kinetic energy can change. I have change in kinetic energy on the micro level. In other words, I have a table right here. There are particles inside the table moving around. I can have a change in kinetic energy of the table if the particles move around faster or slower. And then there's the change in kinetic energy on a macro scale. We just, you pull a speed gun or a motion detector and you figure out how it's moving. Now, changing energy in the micro scale, which is tend to be where we are in this section. The macro scale, this is more in chapter 7. The micro scale will sometimes lead to a change in temperature or a change in length and or a change in area or a change in volume. Ultimately, and I'm not going to go through the derivation for this, but temperature is just an average kinetic energy of particles. So if you went up into the thermosphere, something like blanking on the atmospheric thing. Thermosphere is the one right before space. Anyone done this more recently than I have?
I think so. The
Okay.
troposphere is like closest, right?
Say it again?
Troposphere is like the closest one, and then,
To where we are?
yeah.
Maybe. It's been a number of years since I had to deal with that. In the thermosphere, the temperature is incredibly high. But if I were in some device and I stepped out in the thermosphere, I'm probably not gonna burn up. And that's because there's not a lot of molecules up there. And they're zipping around really fast, so there's a high kinetic energy, but there's just not many particles. I'm more likely to suffocate to death than I am to burn up. Now, if a particle hit me, I probably wouldn't even notice. I'm not gonna test it. And as the particles start moving around, if they move around more actively, they can start to get farther apart from each other, still staying in solid form or liquid or whatever form they're in. And in which case, we can start getting changes in the dimensions, the length of it or the area of it or the volume of it. The reason for cracks in the sidewalk. Now, potential energy, if there's change in potential energy, we are going to see this in thermodynamics through a phase change. The delta phase. So solid to liquid to gas to plasma, etc. That dramatic pause there was for questions. There were. All right, let's explore this. So if we're dealing with a change in temperature, in other words, if it's getting hotter, that means the particles on average are moving around faster. Getting colder, on average, the particles are moving more slowly. So first, let's talk about our temperature scales. There are, I was about to say 4 common temperature scales. There's actually 3 common temperature scales and then one that has been left in the dust. Give me a temperature scale.
Fahrenheit.
Being pedantic, degrees Fahrenheit. Pardon? Degrees Celsius, or I will sometimes say centigrade, because I was taught back when it was called centigrade. You probably not.
I was first in the grade.
You were taught centigrade too?
No, it was both.
You got both, okay.
Kelvin.
Kelvin. And the fourth one, the one that they just simply don't teach anymore. It's a chance for bragging here. Who's got it? My effort to somewhat keep it alive, Rankine. I feel bad for Rankine. I mean, he finally gets a unit named after him. His family's probably really happy, or his ancestors really happy, and then it just basically, no one uses Rankine anymore. I'm gonna do a little bit of math here, some graphing. If you remember slope-intercept form of a line, then you're golden. If you don't remember it, but if you've been doing graphs, you know you've seen it. I know you've seen it. So I'm going to put degrees Fahrenheit over here and degrees Celsius right there. What is freezing on the degrees Celsius scale? What is boiling? I guess technically temperature in degrees Celsius, temperature in degrees Fahrenheit. This would be temperature in degrees Fahrenheit versus temperature in degrees Celsius. What is freezing in the degree Fahrenheit scale?
32.
So 0 and 32 meet, and what is boiling in our current system?
212.
So if I draw a line connecting it, that basically is a line that converts from one to the other. So if I think about y equals slope x plus b, my y is just my degrees Fahrenheit, my x is degrees Celsius, b is my intercept here, my vertical intercept, which is 32, and my slope, well, rise over run. I go from 32 to 212, that's 180. My run is 100, so my slope is 180 over 100, which is, doing the fancy math, 9/5. So we have a formula here that converts from degrees Celsius to Fahrenheit. What is Kelvin, though? I mean, degrees Fahrenheit, we've been living with, for most of us, all of our lives. Degrees Celsius, some of you might have dealt with that at some point in your lives. But degrees Celsius is very common in Europe. And, the Fahrenheit or Celsius?
Degrees Celsius.
Okay, we seem to have a consensus. What's Kelvin, though?
Isn't Kelvin for like really hot stuff?
That's exactly what
The other direction.
Really cold stuff?
Yeah.
And really cold is hot.
There's an inverse Kelvin that sometimes, that I have run into, just whatever Kelvin would do, they basically took, which is the unit of 1 over the temperature in absolute scale. In which case, it gets smaller as things get hotter. But that's just a side thing. So if we go back to that, temperature is just the average kinetic energy. So if things start slowing down to the point where everything stops moving. So if the kinetic energy of every particle in the system, or in the room, or in the jar, or whatever we're working with, if all those particles stop moving completely, that's gonna be as cold as it gets. And that's what they said. They said, all right, if that is as cold as anything can get, as everything stops moving, we'll come up with a scale, and we're gonna set that at 0. And so they did. So 0 Kelvin, and no, it is not 0 degrees Kelvin, it's just 0 Kelvin, is negative 273.15 degrees Celsius. So to convert back and forth, you just add 273.15, or if you're feeling saucy, 273, and you can go from Kelvin to Celsius, or Celsius to Kelvin. If you add 273, that'd be Celsius to Kelvin. There is a lab, I haven't done it since the pandemic, probably gonna wait another year, but there is a lab where we actually do try to figure out where this 0 Kelvin is in terms of temperature Celsius. If you take a straw, just ordinary drinking straw, and you put water in it, cap the end, and then flip it over, you'll get an air bubble with water on top of it. As you cool it or heat it up, the air is going to expand more than the water will. So if you heat it up, the air will start to expand to indicate a higher temperature, and if you cool it down, the air column will start to shrink. And so you take some known temperatures, and then you sort of extrapolate backwards to at what point would the air be 0. In other words, all the air molecules stop moving, and at that point, it takes up no space at all. Where would that end up? That's the lab. It works really well or really horribly. There's not a lot of middle ground on that lab. So you're welcome, or I'm sorry, depending on which way we've gone.